Hello, and welcome to my first ever blueprint on Dynamic Programming, Part 1, the Longest Increasing Subsequence. Now I've just finished my master's program, and I thought it would be great to clean up some of my notes and share them with you to hopefully aid you along your academic and professional journey. Now these topics can be highly academic, so I found it best to relate to them by taking a look at some real-world applications. Take for instance the stock market. Imagine we're looking at some window of price action and we would like to find the number of consecutive higher highs for a particular stock, like Nvidia. Now let's say we're looking at a 1-week window of price action. We can use LIS to find us higher highs within this window that may look something like this array. Now why would we be interested in something like this? Well, we can use LIS as an indicator for bullish momentum of a stock. So this was for a 1-week performance that set an LIS size of 4. But what if I told you another window of an entire month set the same exact LIS score? How would we distinguish between these two LIS results? Well, we can further enrich our LIS algorithm by including a gap penalty for every element we skip over, in which our final result will be something smaller than this size 4 in this example. Now that we have this example here and we are familiar with it, it is important to note some subtleties about LIS problems. There are 3 major variations that we could ask for. The substring, which is where we are looking for consecutive elements within an input array without any skips. There are a few answers within this sample array, but they're all of size 2. Then we have the classic subsequence, which is the most common LIS problem definition, where we're allowed to skip over elements of the input array. This was of size 4 as shown above. And finally, we have the non-decreasing subsequence, in which we are okay with taking equal values, such as the 752 in this example, that results with a size of 5 LIS. There are many more really great examples of where LIS comes in handy, such as DNA sequencing, where we use LIS to aid in database queries of a particular protein sequence we're trying to look for. Or in manufacturing, where we're trying to determine the tool tolerance divergence before the assembly line has to be shut down for maintenance. Okay, so we have some context for what LIS is and its variations, but how do we go about programmatically solving LIS? This brings us to highlighting the differences between dynamic programming and recursion. Take for instance the Fibonacci number that starts with 0, then 1. Then we add the previous 2 Fibonacci numbers together in a series. This looks like a prime candidate for a recursive function. It's nice, it's clean, we even flexed a little bit by properly using recursion. However, there is a catch. Let's detail out what actually happens in the tree. We start with some input and Fibonacci we would like to find. Then the recursive function breaks the problem down into its previous and previous Fibonacci call until we reach some terminal state of n equals 0 or n equals 1. So let's say we want to find the 4th Fibonacci number. We can visually step through this with the graph on the right. We start with n equals 4, then n minus 1 becomes 3, n minus 2 becomes 2, n minus 3 becomes 1, and so on and so forth. Now for clarity, I'm going to write out the rest of the n values of the tree, and then we'll evaluate the function and bubble our answer up. Where n equals 1 and 0, we reach the terminal state of our recursive call. These evaluate to 1 and 0 respectively and bubble up as previous and previous Fibonacci calls. As we make our way through the tree, notice that we've called for the n minus 3 Fibonacci 2 times. We're essentially being asked to do work for something that we've done work for already, and this happens again for n minus 2. As you can imagine, this problem exponentially blows up as we ask for higher and higher values of Fibonacci. This is not only time complex, but also space complex, making it very undesirable for computing the longest increasing subsequence. So now that we have seen why using a recursive function to find LIS is inefficient, wouldn't it be great if we could remove all that duplicate work for things that we've already done work for? Well, this is where dynamic programming comes in. In dynamic programming, we solve the subproblem and use its solution in a recursive manner to solve our bigger problem, thereby preventing the duplication of effort that we saw in the recursive function approach. Let's work through a dynamic programming approach for finding the longest increasing substring. This is the substring where we cannot skip elements in an array A of size n. A proper dynamic programming solution has 4 parts: the subproblem definition, the definition of recursion, the pseudocode, and the time complexity analysis. First, we need to define the subproblem. The subproblem definition at its highest level is really just restating what the problem is asking for up to some intermediate index. For the LIS, this could be something along the lines of let T of I equal the length of the longest increasing substring of array A from the first index 1 to some intermediate index I, including I. This seems pretty simple, but let's make sure we understand what is required of us for a proper definition. A subproblem definition should have 3 parts. First, defining the solution in a table format. This is T of I. Second, we need to restate the problem solution for the input array from index 1 to some intermediate index I. This is the heart of why we call this part a subproblem definition, because we're stating that our table T of I will have the solution for the LIS up to some intermediate index. Now, before I move on, it is important to note that in dynamic programming, the common practice is to start index at 1 rather than at 0. And finally, step 3, which people find the most confusing, is to determine if your subproblem solution includes the solution for I or not. This part is best explained by an example, and in fact, in practice, I would highly suggest writing out a sample to convince yourself that you want to include the ith element in your solution or not. So let's take a look at this array that has 0, 3, 1, 2, and 3 in it. The general idea is that we want to increment our LIS count by 1 every time we have an increase. So let's take a look at including I first. We start with the first element in the input array, which is 0. The LIS for size 1 is 1. The next element is 3, from which 0 to 3 is indeed an increase, so we increment our previous LIS count by 1, resulting in LIS of 2. The next element is 1. This is a decrease from 3 to 1, so we want to reset our count from here on. But you might say, wait a minute, an array of 0, 3, and 1 is still an LIS of 2, and that is in fact true, but this is where the word include really matters. When we say including I, we are really saying our solution includes the ith element as part of the LIS solution. So if we return the array solution for the LIS instead of the count, then stating that we're including the I means that 1 would be the last element in our LIS array solution, which also has the property of being the highest value. For this to be true, the only value solution here that includes 1 as the highest value without any skips is a count of 1. Then the rest is straightforward, but still demonstrates that we are always looking back from the ith element without any skips. So we increment plus 1 from 1 to 2, then plus 1 from 2 to 3. This certainly makes sense, and we can already start to see how we would write out the solution for LIS, but let's take a look at not including I. Well, we would start with the first element, which is 0, but not including this would mean that we would have a count of 0, which is already not what we're looking for as the solution to LIS. Then we move on to the element of 3, but not including 3 is just a size 1 count. Then we have element 1. We finally have our first increase from 0 to 3, but it has nothing to do with our ith location logic. We continue to process the rest of the array to result with the max LIS of size 2 that does not include I. This is certainly correct for the statement of not including I, but on the big picture, it's clearly not the LIS for the input array, which is what the problem is asking us to find. So the correct approach here is to include the ith element in our solution. The reason why it's always good to start with an example problem is because solving it out on paper sets you up for thinking about how the recursive relationship should be formulated. As we saw from our example problem, we wanted to include the ith element in our solution. Thus, we increased our LIS count if our current element value was greater than the previous. Otherwise, we reset to 1. That's exactly what we need to formulate our recursive relationship that's written in a mathematical format. This is a formal mathematical relationship that defines how the subproblem recursively combines to formulate the solution to our problem in a table. So let's step through the key pieces of such definition. First, we need to determine if the initial condition is needed. I always find myself writing an initial condition based on a size 1 input, then go from there. You can always remove it or add some more to it later, but at least I won't forget about it. Again, remember that in dynamic programming, indexing starts at index 1, so our table for a size 1 input corresponds to a t of 1 equals 1. Then we detail out the logic for how we solve the example problem. Well, if our current input element value was greater than the previous, that's a of I is greater than a of I minus 1, we wanted to increase our previous LIS count by 1, so that's t of I minus 1 plus 1. Otherwise, we reset the count to 1 if we have a decrease. Lastly, and this is absolutely key, to not forget about the range where this relationship is applicable. We cannot reach into undefined location of our table, nor can we do the same for our input array. Fixing undefined table location is easy by adding initial conditions, but we cannot fix undefined input locations. This is a rule for dynamic programming in that we cannot mess with the input array. We cannot append or prepend or do anything to the input array to make it work with our solution. So with that said, the proper range for I is from index 2 to n. Since we look back at a of I minus 1, that requires us to start at index 2. If we started at index 1, we would be reaching back to an index 0 that does not exist. It's undefined because, again, in dynamic programming, indexes start at 1. Finally, we write out our final solution to our problem. This was certainly optional in my academic career, but I find it to be more complete and better matches the next step, which is translating the mathematical relationship to pseudocode that does require you to return the final solution. Now that we have formulated the mathematical recursive relationship, it is time to translate it into pseudocode. This step is relatively straightforward because we've already done the hard work of writing out the recursive relationship. The key is to restrain from writing language-specific code. The initial condition is a straight copy over. The recursive loop is a for loop over our range that we've already defined. This is probably a good place to stop and say that writing this as for I in range 2 to n would be incorrect. That is language-specific. More specifically, it's written in Python, and therefore it is not pseudocode. The condition for adding the count or resetting is simply a if-else statement. And finally, we return the solution to LIS, which is the max of our table. We take the max because recall that we're not keeping track of the max LIS at each ith location. So if the last value decreased, then our code would reset to count 1, and thus it is clear that this is not what we want to return. So we take the max here. The last step in proper dynamic programming solution is to analyze the runtime in big O notation. The initial condition assignment is constant time, so that's O of 1. The for loop loops over the input array, which is size n, so that would be O of n. Everything inside the loop, the if-else statement, the addition, is all constant time, so that's O of 1. Then we return the max of our table, which is an operation that requires us to loop over the table array that is also size n, so that would be O of n. So we get a total runtime of O of n plus O of n, which simplifies to O of n. Okay, so we stepped through the LI string solution. Let's see if we can do the same for LI sequence, where we're allowed to skip over elements in the input array. We start with the subproblem definition, where we hit our 3 important steps of defining the solution in the table, restating the problem from starting at index 1 to some intermediate index I, and determining if we need to include the ith element restriction or not. As we saw on the substring, the restrictive including I condition was what we wanted, so let's see if that still works for us here in the subsequence. Given the same example problem of 0, 3, 1, 2, 3, starting with index 1, we have the value 0, that is an LIS of 1. Then index 2, we get the value 3, which is an increase from 0 to 3. So far this is all the same as the substring logic. Now we get to index 3, where the value is 1, and previously on the substring, we would reset t to 1 with a decrease. However, on the subsequence, we're allowed to skip, so we have to look backwards for candidate values to increase from. And we indeed have an increase from 0 to 1, so we increment t from this index, which is 1 plus 1, that yields us this value of t of 2. Then we index to 4 to get the value 2, which may seem like a simple task, but we have to keep consistent logic here. So again, we look backwards and find the previous values that were less than 2, which are 0 and 1. And here's where we get the last piece of logic that we need for the LI subsequence, which is to take the max t of previous candidates that were larger than our current value, which is 2. So we increment 2 plus 1 to t equals 3 at this location. Then we repeat the same logic for the last index to get an LIS score of 4. So now that we have worked out the logic on our example problem, let's see if we can write out the recursive relationship. As we saw in our example, because we're allowed to skip over elements, the logic is a bit different from the substring relationship. We were incrementing t from a previous t if we had an increase, else we reset to 1. Here, because we have to look backwards from our current location, we introduce another loop that we have to keep track of in index j. Let's pick this apart to make sure we understand what's going on here. We start with the initial condition t at I equals 1 is 1, because the LIS of a size 1 array is 1. Then at index 2, we begin our loop all the way to n, but at each iteration of I, we have a subloop to look back at all previous values, not including our current value for candidates. So at I equal 2, j only goes up to 1. Then we perform the check for increasing candidates. That is, a at I equals 2 is greater than a at j equals 1, which is 3 greater than 0, and that is true. So we add this to the candidate max of 1 plus t at j equals 1, and t at 1 is 1. Since there are no other j's to loop over, this simply becomes 1 plus 1 is equal to 2. Then we iterate I to 3, and now j goes from 1 to 2, and we look for candidates. Is a at I equal to 3 greater than a at j equal to 1, which evaluates to 1 is greater than 0, and that is true, so we add it to our max. Then, is a at I equal to 3 greater than a at j equal to 2, and that evaluates to is 1 greater than 3, and that is false, so we do not add it to the max array. And this finally yields a max of 1 plus 1, which is equal to 2. Then we keep looping over the rest of i's and finally take the max of our table to find the longest increasing subsequence. Now we are ready to transcribe our mathematical recursive definition to pseudocode. We start with the initial condition, then we write out our outer ith loop from 2 to n, we predefine our one otherwise term for the current t. Then we look back at previous candidates, that is index j, from start to I-1. We are only looking for increasing sequences, so we apply the filter here, and we keep a running max of the candidates found. We finally return the max of our table, and that is the longest increasing subsequence. The last task for us is to analyze runtime. Each of our loops, at worst case, will run a O of n time. The max function is O of 1. This is important to highlight here, that fixed size max operation in terms of O notation is still constant time, especially here where we are only comparing a running max to the current candidate t value. Then we take the max of our table, which is also O of n. This totals a runtime of O of n times O of n plus O of n, which is simply O of n squared. Okay, so to wrap this up for LIS, here are some key takeaways. There are a few variations of LIS, so it's important to know when you're talking about strings, sequences, or non-decreasing problems. Now, these problems may have seemed specific, but the beauty behind dynamic programming is not memorization of the solutions, but rather the understanding of problem-solving methods that you can draw from. So for Substring, without any skips, graphically, we saw a running max increase of previous t values until we hit a decrease, which reset our t. On the other hand, with subsequences, we utilized a filtered set of previous t values. It is interesting to think about these in terms of short-term memory with substrings versus long-term memory for subsequences. Okay, now for common mistakes. Subproblem definition has a few tripping points where we can accidentally confuse code indexing that starts from 0 with dynamic programming standards that start at 1, or not understanding what include I really means. Again, the simplest way to fix this is to write out an example that we'll need anyway when we are working out the logic for recursion or for sanity checking our work. Now, some literature and academia may teach this differently, but the wording of including I is how I was taught. But just know that up to I and ending with A of I also means the same thing. Moving on to the recursion definition, it is easy to leave off the initial condition because the meat is in the table looping conditioning definition. But if you are referencing an undefined variable, then you're toast, so I always just write it down right away. Another is leaving out the table range definition, for example, when I goes from 1 to n. And finally, writing language-specific syntax in your pseudocode is definitely easy points to throw away, so make sure that the section is properly formatted. Well, that wraps up the LIS in great detail. This was my first video tutorial, so I hope you found it useful. Until next time, cheers.